Let us start this lecture with a thought process. Confrontation calls for considerable courage. It must be exercised to prove a system, not settling a personal score. Let us recall that in the last lecture we derived the governing equation for momentum balance, right. We basically carried out a momentum balance and then governing equation pertaining to that. And today what we will do is basically looked at the mass or the species conservation, right, because already we have talked about mass continuity or the mass conservation, right, and now we will have to look at species conservation. For that we will have to re-look at basically mass transfer processes, right, mass transfer processes. So, let us consider a simple one dimensional situation, right, and it is having a fixed one dimensional flow situation we are considering, and we are having non-reacting mixture, right. These are having non-reacting mixture of what? Let us consider methane, right, gas and hydrogen. This consists of that. Now, we are not talking about any reaction at this moment, just for the simplicity's sake. Okay? There is no production of the methane, or there is no destruction of methane or hydrogen, any one. This is a binary mixture what we are considering for simplicity case. And this, if I say that is a molecule, right, CH4, which is, this is, let us say, molecule is moving with a velocity of, let us say, VCH4, and VCH4, let is the velocity of CH4 molecule, right, with respect to what? Stationary axis, or the, in this case it is a x coordinate system, right, stationary or the fixed coordinate system. Similarly, I can talk about Vs2 is velocity of S2 with respect to coordinate system, and this is what? Only for the x direction we are considering. Okay? We do not have considering 2D, 3D kind of things, just well. And to start with, when you talk about mixture, there will be some mass fractions or mole fractions, right. Let us say consider the YCH4, right, YCH4 is the mass fraction of CH4 in the mixture, and YS2 is the mass fraction of S2 in the mixture, right. That means I want to find out what will be the velocity, mass average velocity, because each molecule, as I told, that there is another hydrogen molecule which is moving a velocity Vs2, that let us say this is moving molecular velocity and with respect to x direction, okay, with respect to x direction. Now, that, and also there, right, there will be also relative velocity, is not it, and there will be some average bulk velocity which will be taken, because both are moving, average velocity will be there. What will be that mass average velocity? Let I say V is the mass average velocity of what? Of mixture, is not it? Yes or no? Now, what is that mixture? How can I find out a relationship for this V? I will be expressing that in terms of individual velocities, right. For example, methane and hydrogen here, I can say Y CH4 into VCH4 plus Y hydrogen and V hydrogen, right. Now, instead of two components in a mixture, if there are n component of a mixture, what will be then average velocity? That means summation of that. So, if I consider that for a gas mixture of n component, the mass average velocity would be V would be summation of Y I V I is equal to 1 to n. Okay. Are you getting? Now, in the similar way, I can talk about molar average velocity, right. Let us say, let V star is basically be the molar average velocity, right. Then for a gaseous mixture of n components, what will be the velocity? Molar average velocity would be summation of x I V I is equal to 1 to n, right. See, there are, and is it V, actually note that V is not equal to, need not to be equal to V star. It may be sometimes, like that is a just a coincidence, okay. Are you getting? Now, the question arises, if I look at a simple molecule which is moving, right, and I can say, let us say this is a molecule which is moving with, let us say this is a methane molecule, okay, let us say, and which is having a velocity, bulk velocity is something, a vector which is having V, and there will be some which will be having a velocity which is called as a diffusion velocity, because it will be diffusing. Let us say there is no flow. If there is no flow, it will be also moving or not. For example, if I put a what you call perfume here, that mass is moving or not, that means that is a diffusion velocity. So, there will be some, let us say, diffusion velocity, I call it as a CH4, and the total velocity what it will be? It will be this VCH4, right. So, let I am coming again to the binary mixture, keep in mind, okay, that is let V star VCH4, this thing is the mass diffusion velocity, right. That is means what? This is the meaning is that this is relative velocity with respect to what? With respect to bulk, you can say, is not it, and which will be equal to VCH4 minus V, yes or no? You can say V, this is a vector quantity, V plus VCH4 bar is equal to VCH. So, that is a thing, and similarly I can write down also VS2 minus V, right. But we will be this thing, but what we will be more interested in the flux, right. So, now let us look at the mass flux, what we will be more interested in, right. If I say that when we talk about this mass flux with respect to stationary coordinate system, right, what will be mass flux of methane. I am considering two cases, right, two components of a binary mixture, right, with respect to fixed coordinate system, right. In this case is the x, one dimensional we are considering, what it would be into rho CH4 into VCH4. And if I consider molar flux, right, of CH4 with respect to same thing, right, fixed coordinate system, will be basically CH4 will be CCH4, C is the concentration and VCH4. And of course, I can write down also in a similar way for the hydrogen, okay, right. For example, I can write down for hydrogen, I can write down for even molar mass flux for hydrogen. Now, if you look at what will be the relative mass flux, mass and molar fluxes of methane will be rho isn't it? And what is this V bar CH4, which is basically relative velocity that we have looked at, and this is CH4 should be density CH4, that will be rho CH4 into VCH4 minus V. And similarly, I can write down of CH4 is equal to C CH4 V CH4 star. Star is always corresponding to what? Molar, okay, and equal to CCH4 into VCH4 minus V. Okay.
So what is CCH4?
CCH4 is the concentration of CH4. When you talk about molar, we talk about concentration, not mass, isn't it? So, now if you look at for ith species, I can write down, right, for ith species, let us say there are n number of species in that means I will have to look at ith species, I means any species. For ith species, I can write down as mass I is equal to rho I V I is equal to rho I V I minus V. Similarly, I is equal to C I V I is equal to C I V I minus B. This is, keep in mind that average, this is right, and these Vi star are different because one is molar, other is mass. Now, if you look at this, right, what I can run, I will take this, let us say I am talking about now, this is equation 1, I can rewrite the equation 1 in a little different way for the methane by using or I can say this is equation 2 and this is equation 1, right, and 2. By using equation 1, we can have, right, mass flux of CH4 is equal to rho I V plus what? Keep in mind that, okay, I am taking this also I am taking as average, this is average, this will be average, okay, fine. Rho I am taking this, what I am doing? I am basically looking at mass flux of CH4. Are you getting this point or not? Okay. If you are not getting, let me do that again. This is average, okay, because this is relative means due to the diffusion, okay. Are you getting? And this mass flux, let me write down here, I am in equation 1. What we did? We basically looked at CH4 average is equal to rho CH4 VCH4 minus rho CH4 CH4 and V, and this is what? This is your nothing but your CH4, yes or no? Yes or no? Right? Are you getting? That is that or not? So, therefore, I am taking this portion to the other side because I want to write down with respect, and this mass flux with respect to what? With respect to stationary system. This is mass flux with respect to fixed coordinate system. Right, and this portion is getting into rho I into V I. I am taking this I. So, oh, sorry, this is CH4. I have already done here. That's all. Like I am taking to this. This is the equation. Let us say this is equation. I can say 3. In the similar way, I can write down for what? For IS species, but let me little bit dabble with that before getting into, that is m dot I CH4 is equal to rho CH4, and instead of V, what I will write down? I can write down mass flux of this into divided by rho, yes or no? I am talking about this term I am taking here. Can I not write down mass flux of this total mass flux divided by rho, and this is nothing but here what? What is that? Y CH4, yes or no? Plus I can write down this CH4 average is equal to, I can write down YCH4 mass flux of mixture plus m dot CH4. What is this mass flux of this? This is nothing but your mass flux of CH4 plus mass flux of hydrogen in this example what we are considering binary mixture, yes or no? Now, that is right. Keep in mind that this will be nothing but that. So, I can write down YCH4 m dot CH4 plus m dot hydrogen, I can write down minus, and what is this term? By the Fick's law? By Fick's law, that is nothing but your minus rho d CH4 hydrogen into what? dCH4 into dx, right. So, therefore, I can write down this as what? M dot CH4, I can write down YCH4 M dot I, right, minus rho CH4 hydrogen dou YCH4 dx. And for ith species, we can have I is equal to yi summation of. So, and what you will do? You can write down, right, I is equal to 1 to n minus rho dij yi dx. Are you getting? This is for ith species. And what it says? It says basically this is what you call mass flux of ith species, right, and this is this term what it calls? It calls basically bulk mass flux of ith species, and this is mass flux of ith species due to what? Due to molecular diffusion. Keep in mind this equation is very important. I can say this equation maybe 4, right? Can I say this as a 4? Just check, right. So, this equation is very important for deriving governing equation for species, right, by dx, and this term is basically due to Fick's law. Already we have derived that, isn't it, right? Make sense? So, this is a very important relationship what we will be using. Okay. I will discuss little bit more about that in the next lecture, then we will derive the mass species conservation equation. Okay. Thank you very much.